haven't made a video for a day or two, so I guess it's time. Guess I better do it now. Okay, we can actually start talking about the beautiful, beautiful Zelevinsky classification right away. But let me say something about supracuspidal representations or cuspidal representations in general, because we're now in position to define them. So, remember last time I talked about there's this process. Well, we have induction, right? And that takes in smooth representation of a closed subgroup. Well, in particular, we have parabolic induction, which is going to take us from a smooth representation of some Levy subgroup, and it will create for us, built out of that, a representation of GLN, or G. I mean, everything I've written here works pretty generally, but we're going to keep it down to earth, GLN. And then vice versa, there's something that's sort of like just restricting a representation to a subgroup, except, just like if we wanted to have some special relationship with induction, since induction, we had to, gussy it up with parabolics and normalization choices. We should expect the same thing for the sort of nice companion to induction. So with that in mind, so let me just write this to remind myself that this is on the left. IPG. So now let's suppose I had some representation of my group G, pi, and I might hope that there's some way to relate this to a representation coming from the Levy subgroup, right? We somehow want to build our representations up inductively in the literal sense as well, right? So I've got this representation pi, and maybe itself is induced. That would be cool. But in at least, in an effort to just sort of relate it to something that is induced, right? So I might like, I'll try and consider some, I don't know what notation I use, but I'll call this sigma, right? So I might try and see, if this was an irreducible, right? Then if there's any element of this Hom set at all, it's going to have to be an injection. Because otherwise, if this was not, right, we would have a kernel here, and that kernel would be a sub-representation, but that's not possible because I'm assuming pi is irreducible, right? We're trying to understand our irreducible representations of a group, and we already know that these are going to end up being infinite dimensional. So this would be the ideal situation, right? If I given some irreducible pi, in an effort to understand it, if I took some representation sigma that I already understand on some smaller Levy subgroup, I induce it, I get this bigger thing, but, I sort of have a very well-defined structure, right? It's collection of, it's a vector space of functions satisfying this invariance property. And the group action is just translation, right? Translation of the function. So that's a pretty concrete description, right? Well, then, if that's the case, by this sort of nice adjunction thing, then what's going to happen is down on the Levy, if I apply my Jacquet, well, I know that certainly if I can find an embedding here, I can find an embedding here, right? So So something I could do, for instance, is I could take my representation pi if I don't yet know that something like this is happening, and in my effort to better understand pi, I could examine the Jacquet modules, right? I could see what happens when I restrict this down to my Levy subgroups and see if I get anything recognizable, or at least maybe I can try and come up with some sort of, map onto or into this representation, right? So if I can find some non-trivial Hom spaces here, then this gives me hope that maybe I can realize my irreducible as being some sub-representation induced from something smaller. The issue is, um, if it turned out that this was trivial, so not the trivial representation, but the zero representation, like the zero vector space, the group acting on the zero vector space. Well, then there would be no hope of finding a non-trivial homomorphism here, and that is to say, no hope of finding a non-trivial homomorphism here. So never mind even thinking about sigma, what kind of sigma I know that's a representation of L, right? If this were to be the case for my irreducible representation pi, then there's simply no hope of getting anything here. And in other words, I simply cannot hope to understand pi in terms of something from a smaller subgroup, at least a smaller Levy subgroup and induction here. So it's somehow really this representation is like native to G, like it really belongs to G and not to its subgroups. It's really something that belongs up at that level, and we're sort of going to be have to be more clever to access it. Well, can this even happen? I mean, you probably presume that, well, I'm talking about it, so it could happen. Or maybe I'm just saying, oh, we better check and prove a theorem. But no, it turns out that it does happen. So if pi is any representation that satisfies this property, which is to say, applying the Jacquet functor for any parabolic gives you the zero representation, then we say it's cuspidal. And if its pi is also irreducible, we say it's supercuspidal. So these things exist. And this kind of represents a bifurcation in the representation theory. So for instance, and this is kind of still the case, what I did, there's sort of two like industries. There's the industry of cuspidal representations and coming up with clever ways to prove that these exist, to actually like construct them and make constructive give like the full exhaustive list of cuspidal representations, right? That's one part of the story. And then the other part of the story is sort of presuming you have cuspidals, doing stuff with those, including induction. Yeah. So fun fact, we've seen some cuspidal representations already. For the torus, a character, again, smooth character, so a locally constant character. This is cuspidal. Why? Well, there's no Levy subgroups to restrict to, right? So this condition sort of vacuously satisfied. And those are all the sort of easy to describe cuspal representations. There's this whole very interesting industry. I don't know a ton about it. Maybe if people ask, I can give references. There's both references new and old that do lots of interesting things. There's stuff like the Vey representation comes up, Bruhat-Tits theory. Um, these things go into the construction types, not to be confused with type theory, the logical foundation, but there's this construction of types. But what we're gonna do is just sort of take this and run with it. So when in doubt, so we're gonna completely black box this theory of cuspal representations. We're gonna trust that our friends working in that area of representation theory have built all the cuspidals we need. And if we ever get, start to feel uneasy because we don't have examples, well, we can just think of characters of the torus. Those will be the cuspidal representations. Great. So with all of that in mind, we are finally ready to begin the Zelevinsky theory. So first, we need to introduce the notion of a segment. So a segment for us, which in Zelevinsky's papers he denotes with delta. Now, to make our lives easier, we could reduce it to just integers and half integers. I'll say something about this at some point. So I'll probably mostly just write those. But also, if we want the most general version, we can take S can be any complex number. Maybe modulo 2 pi I z. If you remember the characters I was talking about before, this will make sense in a moment. So it's just some consecutive run of numbers. So this in fact is going to be an ordered set. And so let's just we'll often denote it with an interval. So I'll do something like AB. So by this, I'll mean, of course, A plus 1, dot, 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 up to some number B. And the point is we're gonna classify our representations of GLN in terms of these segments. So they're like purely combinatorial gadgets, and there's some basic combinatorics we can do on them that tell us when other representations are included in others and stuff. So we're gonna get there in a second. It's so cool. I love it. Yeah. Okay. So we've got our segments, we've got these combinatorial gadgets. How do I assign a representation to them? So step one, so just the basic segment theory would say this. So if I have a segment delta, what I'm going to do is take a representation. Oh, what notion should I use for it? I'm going to say S. Yeah, I'm just going to write an S for now. And the representation attached to this segment is going to be so we're going to induce parabolic induction from the Borel. So this is the subgroup of upper triangular matrices in our group GLN. And in this case, N is going to have to be B minus A plus 1, I believe. Let me think. 1 minus 1, 2. Yeah. And what we're going to do is take our, so remember, nu is our character. And the numbers in the segment are going to describe the twists of our character. And then we're going to take the external tensor product of these. So that is to say, this thing here is the representation of the torus that sends the diagonal thing, TA to TB. The character that sends this to nu of, well, let me write it really, really explicitly. That sends this to the p-adic value of T1 to the power of A times the p-adic value of T2 to the power of A plus 1, ... down to the p-adic value of TB to the, oh, I guess I shouldn't call it B. This is N. Yeah. N to the B. Yeah. Okay. And so it turns out that this representation has, so S delta, it has a unique subrepresentation and it has a unique quotient. In particular, if delta is of the form n minus 1 over 2 and n plus 1 over 2, then the trivial representation, by which I mean like the one-dimensional representation on which GLN acts trivially, the trivial representation is a subrepresentation of S delta, of this induced representation that we've created. In fact, it is the unique, irreducible representation, subrepresentation. So for this reason, I will denote this by Z for Zelevinsky to be the unique subrepresentation of S delta. So in general, if you have this combinatorial gadget, right, this interval defined by two complex numbers, then S sigma, this induced representation, so it's taking these representations we know very well, these characters, you induce it from the Borel. This representation will have a unique irreducible subrepresentation. And I highlighted one particular case where it's the identity. And in fact, in the other cases, we just get twists of the identity. Maybe I'll explain that in the next video. Maybe I'll explain why we get the identity here as well. Let me say, you should be able to see it yourself. And so in this particular case, the way to see it is you might remember this n minus 1 and n plus 1. Remember our modular quasi character was n minus 1 to 1 minus n. Oh, sorry. Yeah, this should be 1 minus n. My mistake. 1 minus n up to over 2 to n minus 1 over 2. And then remember I said that we multiply our normalized parabolic induction has us tensoring by the root of the modular quasi character. So in short, if you expand this out, you write out the tensor product, you see that this corresponds with this, and only in this very particular case where sometimes these are called balanced multisegments, will we see that, so writing this to be the unnormalized version of parabolic induction, we get the representation that's just induced from the trivial representation. And so if you unpack the definition here, where this is functions from G into the complex numbers, where G is acting by right translation, well, certainly, and well, you have to unpack the condition, but what does the condition on the function say in this case? It says f of t for something in the torus, tg, since you just pull out the trivial representation, is g, right? So the point is that certainly constant functions themselves satisfy this. Constant functions satisfy this property. They satisfy our locally constant condition, and they're invariant under this. So it defines an invariant subspace. And since any two constant functions just differ by a complex scalar, we see that we get the trivial representation. Okay, I mostly explained it for you, but I guess if you want me to do write up the details a bit more vigorously, I can do that for you. The other thing that we get, and then bug me if you want me to show that for the non-balanced segments, we just end up getting twists by some particular character here. It's the way that characters work with induction. Well, let me know if you don't figure it out on your own. So there's one other thing I want to mention as well. So unique irreducible representation, you might be used to the fact that in finite group theory that all of our representations can be written as direct sums of all their irreducible constituents. And well, I know some of you aren't because you were asking about modular representation theory, which is the characteristic P theory. But it turns out this isn't always the case in even though we're working over the complex numbers, in our sort of infinite dimensional world, even though we have these nice topological implications. Generally speaking, this representation, S delta, is going to have many, many representations, irreducible subrepresentations in it, but it's an example of what we would call indecomposable. So in fact, it is not the direct sum of any smaller representations, though it may contain many irreducible representations inside of it. Moreover, S delta, much in the same way that it has a unique irreducible representation, which is a sub representation of it, there's also a unique representation that appears as its quotient. And how should I say this? So again, in the case of a balanced segment, so if balanced, the representation that appears here is a very important one. I'll denote it by ST. This is called the Steinberg representation. In particular, let's talk about the case GL2. So GL2. And I'm going to look at the balanced segment, minus 1/2, 1/2. So in particular, I'm going to my S delta. This is the normalized parabolically induced representation that takes minus 1/2, the character that sends the first element in the torus to its p-adic absolute value at minus 1/2, to the second on the diagonal of the torus to its p-adic absolute value to positive 1/2. And when I parabolically induce that, in fact, in this case, the trivial and the Steinberg are the only two that show up. So actually, in this case, if you're familiar with this language, I get a short exact sequence. So this representation in the middle has exactly two irreducibles sort of living within it. One is its unique subrepresentation. The other is its unique quotient. The sub is the trivial representation. And the quotient is the Steinberg representation. So this is an important example. Okay, so this is part one. We've now decided, we've now given away how to, if you have a segment, we've given away to associate to that segment a representation of a very particular GLN. Okay. So that is some progress towards our classification of all the representations of GLN. How so, you may ask? Well, we're getting there. We're getting there. I was maybe going to say this before, but I'm going to introduce maybe two notations for, well, let me say it this way. So now we are going to consider multisets. In particular, we're going to consider multisets of segments. So I'm going to write down a multisegment is just a collection of segments. We're going to impose an ordering on them as well, but it's a set of segments where the same segment can appear more than once. So maybe, for instance, a multi-segment would be, -1/2 to 1/2, -1/2 to 1/2, and minus 1 up to 1. So notice all of these segments are balanced. They don't all have to be balanced. Maybe, let me change the example, and -11 to 17. So this could be our multi-segment, for example. And now, okay, this is going to get maybe a little bit weird. I'm just going to state it, and then that'll probably be the end of this video, and we'll talk more in the future about, we're very close to the actual classification, the statement, and we can start playing around with consequences of it. But now, basically, we've got most of the ingredients to get things which capture all of our irreducible representations. So we're now going to associate to each of these multi-segments another induced representation. So there's two versions. Zelevinsky's original one, I guess I'll talk about that first. I'm going to call it S sub Z, and you'll see why in a moment. So S sub Z of a multi-segment, right? So just some set like this. What do we do? Well, we're going to take first the unique, almost wrote the wrong thing. So suppose this is our multi-segment A. We know that for whatever appropriate size for this one, for the segment delta 1, right? There's some corresponding like GLN1. And we know that through this process of induction, that induction has some unique irreducible subrepresentation. And so we know that through the process above, I'm able to create some irreducible representation of GL. I'm calling N1, whatever the appropriate size it has to be to match, the length of the segment. I suppose if I was really labeling these as, delta I, its first entry is AI, its second entry is BI, then NI would be BI minus AI plus 1. So this is an irreducible representation. I'm going to take that, and I'm going to take the external tensor product, which, now that I'm thinking about it, I don't remember if I explained that to all of you. So if I did not, I thought I did. But let me know. As always, questions, drop questions in the comments below. So I'm going to take all of this. Now, this is a representation of, if I imagine this, well, this is a representation of the group GLN1 cross GLN2 cross ... up to GLNR. And that's a Levy subgroup of GLN, right? It's just, I have to imagine putting those blocks in diagonally. So there's kind of some choices here that we sweep under the rug about how we're embedding things, which is fine. It turns out all these choices work out fine when we eventually talk about the Langlands classification that actually has a version that will help us deal with some of these choices. But just trust me for now that they're fine. So I've taken all of these things. I've produced a representation of the levy, and now I'm going to induce again. So it's now going to be I P for whatever parabolic it is right now. Because of this shape, I've got some who knows what kind of parabolic subgroup I'm dealing with. So I P up to my, oh gosh, what do we call it? I don't know, GL big N, right? So again, I'm going to do normalized parabolic induction. And now this thing, this representation will have a unique irreducible subrepresentation. And I'm going to call that Z sub A. And yeah, I guess that's where I'll leave it. I'm tempted to keep talking, but I should probably go and get some dinner. So, well, okay, I'll tell you one more thing. This is Zelevinsky's original version, and there's a whole story just focusing on the subrepresentations there that appear. I'm also going to write, and you can maybe predict this from my notation, S sub QA, where instead I take those same segments and the appropriate parabolic, but now I instead take those unique irreducible quotients, right? Those Steinberg representations or twists thereof. And I'm going to parabolically induce that up. And now I get a representation of well, a different representation of GLN. Well, presumably, who knows? Maybe they're accidentally the same. They're not. And now this one has a unique irreducible quotient, which I'm going to refer to as QA. Now, you might say, oh, well, doesn't this have a unique irreducible quotient as well? And this will have a unique irreducible sub? Yes, and that has a role to play. But actually, for the purposes of our classification theorem, in terms of uniquely specifying combinatorial data that describes an irreducible representation in like a unique way as some sort of fingerprint, we're going to need to focus on these ones. So I guess I'll leave it for there, and we'll chat about more about this soon. I know I'm flying through some of these things, so yeah, please ask me some questions. And